Hello, this is a MA 166 Spring 2023 exam number 1. So problem 1 says, find the center and radius of the sphere defined by the following equation. The equation is x squared minus 8x plus y squared minus 4y plus z squared plus 6z equals 7. So the general formula for the equation of a sphere can be given using the formula x minus a squared plus y minus b squared plus c minus z squared, z minus c squared is equal to r squared. And that is where a, b, c is the coordinates of the center, and r is the radius. Okay, so to find the answer, to find the solution to this question, what we have to do is we have to take the equation we have over here and then convert it to the standard form for the equation of a sphere. Okay, and so the way we're going to do that is by completing the square. If we look at the problem, you'll notice we have kind of three parts. We have x, we have the y part, and then we have z. So we have to complete the square for each of these, each variable essentially. So an easy way to complete this square here is essentially we have a coefficient of 1 here. So all we have to do is divide the coefficient of the x term by 2, and that is the number that we use to complete our square. And so you'll notice that if I expand this out, I get x squared minus 8x plus 16. And this is almost identical to what we're given in the original problem, except we have an extra constant over here. And later we'll see how we can take care of that. Okay, so we do the same thing for y. Half of negative 4 is negative 2. And if we want to complete the square for a polynomial expression where the square term, so like the x squared or y squared term, has a coefficient that is not 1, the formula we use is negative b over 2a. Or sorry, b divided by 2a. So where b is the coefficient in front of the degree 1 term, and a is the coefficient in front of the b is the coefficient in front of the degree, b is the coefficient of the number of the variable with the degree 1 term, and a is the coefficient of the variable with the degree 2 term. But in this case, our coefficient is 1, so it doesn't really matter. Okay, and so we get, if I expand this, I get y squared minus 4y plus 4. And then we do the same thing for z. We get z plus 3 squared. Okay, and if I expand that out, I get z squared plus 6z. Again, that's the same as the expression in the problem, plus 9. Okay, now the last thing we need to do is we need to find the coefficient on the right-hand side. So an easy mistake to make here would be to say that the number that goes here is 7. However, that's not true because we have an extra 16, 4, and 9. So what actually goes on the right-hand side is 7 plus 16 plus 4 plus 9. So if we add that up, we get 36. Okay, so this means that the center, again, we can go off this formula. The center would be 4, 2, negative 3, and the radius would be the square root of 36. So the square root of 36 is 6, so the radius is 6. And that makes the answer to problem 1 A. Okay, moving on to question number 2. Question number 2 says, find a vector that has the opposite direction to the vector PQ and that has the length 5. We are given that P is equal to -1, 3, 2, and Q is equal to 2, -2, 6. Okay, so the first step here is to find PQ. We're given the points of P and Q, the coordinates. We need to find the value of the actual vector. So the way we find the value of a vector given two endpoints is we take PQ, the arrow starts from P, so that's like the starting point, and it ends at Q, so that's the ending point. So to find PQ, we have to take the end point, so in this case Q, and subtract P from Q. We subtract the starting point from the ending point. So what I'm going to do is I'm just going to put Q on top here, so this is Q, and P on bottom, and I'm just going to subtract. So 6 minus 2 is 4, -2 minus 3 is -5, 2 minus -1 is 3. So that means the value of PQ is 3, -5, 4. Okay, so we have PQ. Now, parts A and B of the question says find the vector that has the opposite direction to the vector PQ and that has length 5. So, let's tackle the second condition first. In order to get the vector that has length 5 that is in the same direction or opposite direction as PQ, what we have to do is first we have to find the magnitude of PQ. Okay, and the way you find the magnitude of the vector is you take the square root of the sum of the squares of each coordinate. So in this case, the square root of 3 squared plus 5 squared plus 4 squared. And that is equal to the square root of 50. Okay, so that means that the length of PQ is the square root of 50, and to get the vector that has the same direction as PQ but a length of 5, we just have to divide PQ by the square root of 50 and then multiply by 5. Like dividing by the square root of 50 scales PQ down to a vector with length 1, multiplying by 5 scales it back up to a vector that has length 5. Okay, now we can tackle the first condition, which says that the direction has to be opposite of PQ. And that's actually really easy. To get a vector in the opposite direction, all we have to do is multiply by -1. So that the vector in this case would be -5 over the square root of 50 times PQ. The square root of 50 can be simplified to 5 root 2. So I get -1 over square root 2, and PQ is 3, -5, 4. So this is our final answer, which means that the answer to question 2 is C. Alright, moving on to question number 3. Question 3 says, find an equation of the plane passing through the point 2, 1, 5 and perpendiculars to the planes 3x plus y minus 5z equals 2 and negative x plus 2y plus z equals 7. All right. Okay, so the first thing we want to do is let's consider the second statement over here. We can find, so for a plane, for any given plane, it's going to have two vectors that are perpendicular to that plane. And for an equation in this form, finding that vector is really easy. So so for the vector that is perpendicular to the plane 3x plus y minus 5z equals 2, that is the vector 3, 1, negative 5. And you'll notice that it's just the coefficients of the x, y, and z variables respectively. And this only applies when we have the equation of a plane in its standard form. So the reason this is true is actually really simple to see. Suppose we have 2 points on a plane. We have A, B, C is 1 point on the plane, and U, V, W. That's another point on the plane. Actually, I'm going to change this a little bit. So I'm going to say we have point U and we have point V, and U has the coordinates U1, U2, U3, and V has the coordinates V1, V2, V3. And so that would mean the vector UV lies on the plane. Okay? So if U and V both lie on the plane, then 3 times U1 plus U2 minus 5 times U3 equals 2, and then 3 times V1 plus V2 minus 5 times V3 equals 2. And so now I'm going to subtract these 2 points from each other. 3 times, I'm going to subtract the first equation from the second one. So then I get 3 times V1 minus U1 plus 1 times V2 minus U2 minus 5 times V3 minus U3 equals 0. And so it's worth mentioning that the vector UV is equal to V1 minus U1, V2 minus U2, and then V3 minus U3. Okay? And so essentially, this equation over here, that is equal to the dot product of the vector 3, 1, negative 5 times UV. And when the dot product of two vectors is 0, that means they are orthogonal or perpendicular. So that is essentially the proof of why we know that 3, 1, negative 5 is perpendicular. Is perpendicular to this plane. And the same logic holds. I used 3, 1, negative 5 as our example, but we could do the same proof for a generalized plane, and this would still hold. So that's how we know that negative 1, the vector negative 1, 2, 1 is perpendicular to negative x plus 2y plus z. The plane negative x plus 2y plus z equals 7. Okay, so that is important information. Now that we know this, it's a little harder to see the second part of how do we find the equation of the plane that is perpendicular to the two other planes, as well as passes through 2, 1, 5. So I'm going to try drawing a picture. So suppose this is our first plane, and then we have our second plane, or maybe, okay, and I have one perpendicular vector, and then I have a second perpendicular vector, and let's say this is our point P. Okay, and so that means that I could draw a line here, and this triangle that I've drawn in red is our third plane. And just like how we found, okay, and then suppose that this third plane has, let's consider the vector that is perpendicular to this plane, this red plane over here. So if I can find the vector that is perpendicular to, I'm going to also call this plane P, then using the same strategy that I used here, where I found out that vector 3, 1, negative 5 is perpendicular to this plane, if I find that perpendicular vector, I can find the formula for the equation of this plane. So basically, I just need to find the value of the vector that is perpendicular to this plane. But I don't know the plane yet, and so the way I'm going to do that, instead, I'm going to find, so I have two vectors. I have the two vectors that are perpendicular to the two planes given to us in the question. So what I can do is I can find the vector that is perpendicular to the two vectors, 3, 1, negative 5, and negative 1, 2, 1. So how do I find the vector that is perpendicular to those two vectors? I take the cross product. So cross product, and the easiest way to take the cross product of two three-dimensional vectors is the shoelace method for me. So, okay, so I write the two vectors basically on top of each other. So first we start off with this, the last two columns. We take 1 times 1, so that's 1, and then subtract minus the other diagonal, so negative 5 times 2. So minus 10, that's plus 10. Okay, then I do the shoelace. So now I consider the outside two columns. So I take negative 5 times negative 1 minus 3 times 1, that's 3. Okay, and then I consider the first two columns. You take 6 minus negative 1, so that's plus 1. Okay, so I get 11, 2, 7. So this vector, 11, 2, 7, is perpendicular to 3, 1, negative 5, and negative 1, 2, 1. And it is also the vector that is perpendicular to the plane that they are asking us to find in the question. So the last piece of information I need to use is that 2, 1, 5 lies 2, 1, 5 lies on the plane in question. So we're going to have something of the form 11 plus 2 plus 7. Oops. Okay. And so now we don't have to do anything fancy. They give us that P is equal to 215, right? So we can just say that the equation, the formula for this plane is 11 times x minus 2 plus 2 times y minus 1 plus 7 times z minus 5 equals 0. And yeah, and just to clarify, we use the same fact that I proved over here, that the perpendicular vector to a plane can be given by the coefficients of the x, y, and z term. So that's why I put 11 on the outside of 11, 2, and 7 on the outside of each of these parentheses. So this is the final answer, and that means that the answer to question number 3 is C. Okay, moving on to question 4. Okay, question 4 says find the orthogonal projection of u onto v, where u is equal to 1, -3, 2, and v is equal to 3, 1, 5. Okay, so first, let's understand what they mean by orthogonal projection. So suppose I have my two vectors, u and v. Orthogonal means perpendicular. So basically, an orthogonal projection, let me make vector u a little longer. Okay. So an orthogonal projection, we can think about dropping a perpendicular vector from the end of u to vector v. Okay, and this is and so the new vector that I get by drawing a vector from the origin to this point where the perpendicular line meets v, this is the orthogonal projection of u onto v. Okay. So if you understand this, basically we can use geometry to figure out the value of this projection vector. Okay, so first let's say that the angle between vectors u and v is theta. So using trigonometry, the length of the projection vector would be the length of the hypotenuse, which is the magnitude of u, times cosine theta, because this is the adjacent side. So the magnitude is equal to the magnitude of the projection vector is equal to the magnitude of u times cosine theta, and then the other piece of information we need is the direction. So this is the magnitude, and then the direction is v, because as you can see, both vectors are pointing in the same direction. So the only two pieces of information you need to describe a vector is direction and magnitude. So now that we have both pieces of information, we can find the value of the vector. Okay, so first thing, we have the magnitude, and we multiply this by v. However, we have to divide by the magnitude of v as well, because right now the length of vector v is not 1, or maybe it is 1, but to make sure the magnitude of the projection vector is this value, we divide by the magnitude of v, and that means that this component has length 1, and then we scale up that vector by this much. Okay, so basically this is the formula for the projection vector. However, in the problem, they do not give us the value of theta. The key here is to notice that this looks very similar to a part of the formula for the dot product. So the dot product, one of the definitions is that u dot v is equal to the magnitude of u times the magnitude of v times cosine theta, where cosine theta is the angle, where theta is the angle between u and v. So what we can do is we can multiply the magnitude of v on both the top and the bottom. Okay, and essentially we get u dot v over the magnitude of v squared times vector v. And this is the formula for the projection vector, which you should have memorized, but if you don't, you can also do a quick derivation like I just did. Okay, so now we have everything we need to find the answer. So first, we need to find u dot v, and I mentioned one formula here, up here. The other formula is way simpler, and it involves multiplying the corresponding coordinates, so like the first coordinate, the second coordinate, the third coordinate, and then adding up each product. Okay, so for u dot v, what I would do is I'd multiply the x coordinate together first, so 1 times 3 plus negative 3 times 1, so I multiply the y, and then I multiply the z. So the z coordinate is 2 times 5. Okay. And for the denominator is the magnitude of vector v squared. So we can find the magnitude of vector v by taking the square root of the sum of the squares of each coordinate. So the magnitude, we take the square root of 3 squared plus 1 squared plus 5 squared. And then that's all multiplied by v. Okay, now if I simplify this out, I get 10 in the numerator and 10, and then 9 plus 35 in the denominator times v. So that means that the answer, so this is the final answer. This is the orthogonal projection of u onto v. So that means the answer for question 4 is A. Okay, moving on to question 5. Question 5 says, we have the following 4 points A, B, C, D in the 3 space. Point A is 1, negative 2, 3. B is 4, negative 1, 3. C is 5, negative D, 4. And then 6 is negative 3. D is 6, negative 3, 5. And it sets vector U is equal to AB, V is equal to AC, and W is equal to AD. Okay. So, first thing we need to do is we need to find the value of U, V, and W. The way we can find the value of U, V, and W is we take the end point of the vector and we subtract the coordinates of the starting point from the end point. So for example, for AB, I would take 4, negative 1, 3, and subtract the coordinates of A from those coordinates. So this is B and this is A. And if I subtract, I get 0. Negative 1 minus 2 is 1, and then 4 minus 1 is 3. So that means that U is equal to 3, 1, 0. I can do essentially the same thing for the other two vectors. I get 4, 0, 1, and 5, negative 1, 2. Okay, and basically this question wants us to decide whether U, V, W are coplanar or not coplanar. Or well, whether the 4 points are coplanar or not coplanar. Yeah, and that's essentially the same as proving that u, v, w are coplanar. Okay, so the formula that they use in this question is u dot v cross w. And so the, I guess, theorem states that if vector u dot v cross w is equal to 0, then vectors u, v, and w are coplanar. So that is the theorem. All we have to do now is calculate the value of, I should first, it's if and only if. So, okay, so if the value of this expression is 0, then the three vectors are coplanar. If it's not 0, then the three vectors are not coplanar. Okay. Yeah, so before I go ahead and calculate that, I'll do a quick explanation of why this is true. Okay. So, suppose I have 4 points. So this could be A, B, C, D, and it's vectors U, V, W. Okay. So we can envision, so we have V cross W as our first vector, right? Okay, this is V cross W. Okay? And so if V cross W, if the dot product of this V cross W and, I made a mistake here. Yeah, if the dot product of V cross W and U is 0, that means that the angle here would be a right angle. And we know by the property of the cross product that the cross product is basically the vector that is perpendicular to both the vectors that you're finding the cross product of. So we know that this vector is perpendicular to W and V. If this vector is perpendicular to U as well, that means that V cross W and U also has a right angle between them. And so that means that if all three of these vectors have a right angle with V cross W, that means that they must all lie on the same plane. So that's how we know that that's how we prove that this statement is true. And this is also a kind of a visual understanding of why we do this. Why this statement is true. Okay, so now that we know that, we just have to calculate this value over here. So first we find the cross product of V and W. So one way we can do that is using a determinant. So the first row of the determinant is I, J, and K, where I, J, K are the fundamental vectors, I think that's what they're called. Like I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. Okay. And then it doesn't matter what order I put the two other vectors. Okay. Now the formula for a determinant is as such. And this is just something you have to memorize, kind of. Okay. Yeah. And then, so that's how we go from a 3 by 3 vector. Now we have 3 by 3 determinant. Now we have 2 by 2 determinants, and the way you find a 2 by 2 determinant is you find the product of each diagonal, and you subtract the diagonal that goes left to right, I guess. The diagonal that goes this way. You subtract that from the other diagonal. So, for example, here we'd have I times 0 times 2 minus negative 1 times 1. Okay, minus j times 4 times 2 minus 5 times 1 plus k times 4 times negative 1, so negative 4, minus 0. And that is equal to I minus 3j minus 4k. Okay, and that is equal to the vector 1, negative 3, negative 4. Okay, so now the second step is we take the dot product of this vector we just calculated and u. So the dot product of u times is equal to 310 times 1, negative 3, negative 4. And the dot product is a lot simpler. We just take corresponding coordinates, find their product, and then add up all of the products. So in this case, we take 3 times 1 plus 1 times negative 3 plus 0 times negative 4, and that is equal to 0. So since the value of u dot v cross w is equal to 0, we know that the answer has to be D or E. And according to our theorem over here, if the dot product is 0, then the three vectors are coplanar. And if the three vectors are coplanar, that means A, B, C, and D are also coplanar. So the final answer to question number 5 is D. Okay, question 6 says, consider the region in the third quadrant bounded by the curves y equals 3x, y equals x squared minus 4, and y equals 0. Choose the right formulas to compute the area of the region in terms of x and in terms of y. Okay, so the region they are talking about is over here. Let's do in terms of x first. We're usually used to computing the area of a region in terms of x. So let's do that first. So the three curves we have to think about are the curves y equals 0, y equals x, this is y equals 3x, and then y equals x squared minus 4. So one piece of information we need is the value of this point. And we don't actually have to do a lot of work. We can just use the graph they give us to figure out that that point is negative 1, 3. Oh, negative 1, negative 3. And we could also just double check that by plugging in that point into both of these equations. And you'll see that this point satisfies both equations. So yes, that is in fact the intersection point. Okay. So yeah, we have the intersection point now. And what we need to do is we need to split this region up into two areas. So for part 1, we're going to have two integrals. So one is the region bounded by y equals 0 and y equals 3x, and the other is bounded by y equals 0 and y equals x squared minus 4. Okay. So let's go left to right. Let's start with this region first. So the top curve is y equals 0, and the bottom curve is x squared minus 4. So what goes in our integral is 0 minus x squared minus 4. So it's 4, or it's negative x squared plus 4 dx. And then the bounds of this region is from -2 to -1. So that is the lower and upper bounds of our integral. Okay. Now we consider the second part. The top curve is 0, y equals 0, and the bottom curve is 3x. So we take 0 minus 3x. This is really important. Like an easy mistake here would be to just say, okay, this is our y-axis. We just put x squared minus 4 into one integral and 3x into another. That would be a really easy mistake to make. We don't want to do that. So yeah, that's why we have -3x. Okay, and then the last thing we need is the bounds. So the bounds is from -1 over here to 0. Okay, and that is the answer to the first question. Okay, and then now the second part says to find the area of the region between, to find the area of the region in terms of y. So I'm going to erase all this. Now we're thinking like this way. So what first thing we need to do is we need to rewrite our formulas to be in terms of x. So we say x is equal to 1/3 y. X is equal to the square root of y plus 4. And yeah. And now we think about going from negative to positive, right? So we're going this way. And basically, you want to think about taking like all of this and just rotating it sideways so that basically, yeah, if you rotate it sideways, you can still think about essentially doing this, essentially just pretending that you're doing normal integration in terms of x, but you're actually doing y, but you've turned the graph upside down to make things easier, turn the graph sideways to make things easier to visualize. Okay, so in this case, we do not need to split our region into two parts, because the part on top is x equals 1/3 over y, and the part on the bottom is y plus 4. Okay, and so first we have to consider the bounds of our integral. So that the lower bound is -3 and the upper bound is 0. So we have -3. We have -3 to 0. And then we take x equals 1/3 y. Okay, and I made one slight mistake. So I said x equals y plus 4 here. It's actually supposed to be x is equal to -y plus 4. Yeah, and this is a really like small mistake that is like tricky to see why. The function y equals, the function x is equal to the square root of y plus 4 would be this curve that starts over here and goes this way. And clearly that's not what we're looking at. We're looking at the opposite, which is x is equal to negative square root of y plus 4. So yes, the actual function is x is equal to negative y plus 4. And again, that's because when it comes to functions, there's only one answer to the square root, which is positive. We only consider the positive square root. Okay, so I get 1/3 y minus negative square root y plus 4. So that's plus the square root of y plus 4. And this would be the answer to our integral in terms of y. So now we just have to look at the answer choices. which means that the correct answer to question number 6 is C. Okay, moving on to question 7. Alright, question 7 says, choose the right formulas to compute the volume of the solid obtained from rotating about the line x equals 3, the region given below, using the washer method and the shell method. Okay, so the region in question is bounded by y equals x squared, x equals 2, and y equals 0. So this is our region, and we're going to rotate it this way, about this line over here. Y equals, or the line x equals 3. Okay, so first let's discuss what the washer and shell method are. Okay, let me use an example, basically. Okay, let's say we have some area like this. Oh, okay. Or let's make it even easier. Okay, let's say I have this triangle shaped area, and I'm gonna rotate it about the the y-axis. Okay, so I'm gonna rotate it this way. Okay, so the two methods I can use are the washer method and the shell method. So let's start with a washer method first. The washer method basically takes the original 2D solid that we're rotating, and we consider, in this case, horizontal strips. And once I rotate these horizontal strips, I'm going to end up with a flat disc. Okay, so if I rotate that top strip, I get like this really thin disc. But if I rotate the bottom disc, I'm gonna get something that's more like, that looks more like this. And basically, you do that for like each tiny strip in the 2D area, and then you add up the areas of all of those washers. And that is how you find the volume of the solid. So that's a washer method. The shell method says instead, let's consider a vertical strip. Now if I rotate this vertical strip, instead I end up with a cylinder. Okay? And let's say I took like another vertical strip, I'd end up with a smaller cylinder. And you do similar concept, you do that for every single vertical strip in this area, and then you add up the surface area of all of these cylinders or shells. That's shell method. So yeah, that's a basic premise of each method. So first let's start with washer method. So for the washer method, for the washer method, I'm going to be rotating this like a horizontal strip about the line. And since we're adding washers, a washer is basically a circle with another circle taken out of it. So the formula we use for the washer method is pi times r squared minus big R squared minus little r squared dx. Okay? Or, well, dx, dy depends. But in this case, the length of our radius is going to be varying while we're going up the y-axis. So, or wait. Yeah, it's going to be varying while we're going up the y-axis. So it's going to be dy. Suppose we were instead rotating this way, it would be dx. Okay, so now all we have to do is we need to find the value of big R. Big R is the distance from this curve to the line x equals 3. And little r is this distance over here. So that's really easy. Little r is just 1 because the distance between x equals 2 and x equals 3 is constant. So pi, okay, we know that this is -1. Now we need to find the distance between the line x equals 3 and y equals x squared. But first, since I'm integrating with respect to y, I'm going to rewrite y equals x squared in terms of x, so I get x equals the square root of y. And then that means that the distance between this curve and this curve is 3 minus square root of y. So I get 3 minus square root of y squared, minus 1 squared dy. And the last thing we need to do is find our bounds of integration. So we're starting down here from y equals 0, and we're going all the way up here to that point, this point over here, which is y equals 4. Okay. All right, so that is the formula for problem 1. Part 2 is the shell method. So like I said, instead we are going to be rotating vertical strips, and we get like cylindrical shells instead. So since we are rotating this way, we're going to be using the surface area formula, which is 2 pi r times L. So 2 pi will go on the outside, and then r times L, in this case, is going to be dx, since our values are going to be changing with respect to x. Okay. So the length is easy. The length is just the distance between this curve and the y-axis. So the length is just x squared. The radius is the distance between our point x and the line x equals 3. So the radius is just 3 minus x. And then we have dx. And then the last thing we need to consider is the bounds. The bounds is from x equals 0 to x equals 2. Okay. So now we have our final answers, our formulas for the washer method and the shell method. So now we just have to compare which answer choice does that match to. And it matches to C. So C is the correct answer for problem 7. Question 8 says, there is a small planet X which has the shape of a sphere with radius 100 kilometers. Countries A and B occupy the northern hemisphere, with country A ruling the northern cap of height h, including the North Pole, and country B ruling the rest. The areas of these two countries are the same. What is the height h? Okay, so this problem is asking us to find surface area. So what we want to use to solve this problem is we want to use the formula for surface area of revolution. So surface area of revolution basically is it's a method / formula for if you're given a two-dimensional arc and you rotate it. Surface area of revolution basically finds the area of the surface area of this rotated shape. Okay, so the formula for this is f of x times 1 plus f prime of x squared dx. And so this would be if you were rotating about the x-axis. If they were telling you that you're rotating about the y-axis, you would have f of y instead. But this formula is for the case where you're rotating about the the x-axis. Okay. So now what we want to do is we want to think of this sphere cap as a result of rotating this segment in red about the x-axis. So what I can do is I can imagine this sphere as a two-dimensional circle instead. And this part over here is a sphere cap, which has a height of h. Okay, and since the sphere has a radius of 100 kilometers, the center of this circle is going to be 100, 0. So now what we can do is we need to find the formula, the equation for this semicircle. So the general formula for a circle is x minus the center, the x coordinate of the center, so in this case that's 100 squared, plus y minus the y coordinate of the center, which in this case is 0, and the number that goes on the right hand side is the radius squared. So the radius squared is 100 squared. Okay. And so if I simplify this all out, I get x squared minus 200x plus y squared is equal to 0. And so now I need to solve for y. And if I do that, I get y is equal to the square root of 200x minus x squared. So in this case, f of x, which describes this red line segment over here, f of x is the square root of 200x minus x squared. Okay. So now for our formula, we need f of x, but we also need f prime of x. F prime of x, so to do that, I'm going to rewrite this as 200x minus x squared to the power of 1/2. Now I can use the power rule. I get 1/2 of 200x minus x squared to the power of negative 1/2. And I need to take the derivative of this inside portion. The derivative of that is 200 minus 2x. So all in all, this simplifies to 100 minus x over the square root of 200x minus x squared. Now all I have to do is I have to plug in f of x and f prime of x into the formula. Okay. So f of x is 200x minus x squared times 1 plus 100 minus x squared over 200x minus x squared. And if I simplify this out, what I am left with is 100 dx. And I actually made a small mistake. The formula for surface area is all of this times 2 pi. So over here I need 2 pi and I need a 2 pi in front of the integral. So yeah, 2 pi. And at the very end I will explain where this formula comes from. I'll give a quick explanation of how we have this formula. Though you still have to memorize it because this is not something you can derive on the spot. Okay. So now that I have this, the antiderivative would be 2 pi times 100x plus c. Okay, so essentially 200 pi x plus c is our antiderivative. And now all we have to do is we have to consider the upper and lower bounds. So we're actually going to have to do this twice. Once to find the area of this whole region over here. So if we revolve this whole region, we find the area of the northern hemisphere. And if we revolve just this, we find the area of country A. So we want to find the total area of the northern hemisphere, and we also want to find the area of the just the sphere cap. So I'm gonna write AT. AT is total area, and we get that by plugging in 0 as a lower bound and 100 as the upper bound. And I get 2 times 100 squared times pi. Okay, so that is the total area of the sphere cap. Okay, not the sphere cap, the total area of the hemisphere. The area of the sphere cap, which I'm going to say is AS, is 200 pi x from 0 to h. So what I get is 200 pi h. And so in the problem, we're told that area A and area B have the same area, which means that the area of country A is half of the area of the total hemisphere. So that means that AT equals 2 times AS, which means that 2 times 100 squared times pi is equal to 400 pi h. And if I solve for h, I get h is equal to 50. So the height of the sphere cap is 50, which means the answer is C. Okay, so the last thing I'm going to do is explain the intuition behind the formula for surface area of revolution. So this actually works a lot, very similar to the formula for arc length. And if you'll notice, this expression over here is the same expression we use to calculate arc length. So what we do is just like how we do Riemann integration for any given arc, we consider splitting up. We split up the arc into different segments like this. Okay, and we consider what happens when we revolve just these individual line segments. So what we'll end up with is we end up with a frustum. And a frustum, it's kind of like the bottom of a cone. So the surface area of a frustum, the lateral surface area of frustum, is equal to 2 pi times r1 plus r2, where r1 is this radius over here and r2 is the radius on the bottom, divided by 2 times L, where L is the length of the side of the frustum over here. So this is L. Okay, so that's a formula for a frustum. And so what we want to consider is what happens as we make the length of the height of these frustums smaller and smaller and smaller and smaller. Well, eventually, R1 and R2 become about exactly the same, which means that the height R1 can be given by f of x. So we'll have 2 pi. 2 pi stays the same because that's a constant. This becomes f of x, because we have f of x plus f of x divided by 2, that's f of x. And then the length, well, the length can be approximated using the arc length formula, which is 1 plus f prime of x squared. And so that's how we get from the surface area of frustum to the formula for surface area of revolution. That's not a super rigorous proof, but that is the intuition of where this formula comes from. But yeah, you should still memorize this formula because it's not easy to derive on the spot. Alright, moving on to question 9. Question 9 says, use integration by parts and compute and choose the right answer for the indefinite integral of x to the power of 2023 times natural log of x dx. Okay, so first of all, what is integration by parts? Integration by parts says that for the integral u dv, this integral is equal to u times v minus the integral of v du. Okay. So, when we do integral by parts, basically, integration by parts is, we want to start by figuring out what's going to be u and what's going to be dv. So, in our original expression that they give us, we need to figure out what are we going to set as u and what are we going to set as dv in order to come up with a simpler integration, so simpler integral. And basically, we want to make dv something that is easy enough to find the antiderivative of, and we want to make u the other thing. So in this case, we want to make u equal to natural log of x, because if we make, we want to make dv, we want to make u natural log of x. Okay, and the reason is, suppose we did make dv natural log of x. Okay, now what happens is, to solve for v, I need to find the antiderivative of natural log of x, and that is not easy. So that's why we make u equal to natural log of x. That means that dv has to be x to the power of 2023. And the antiderivative of x to the power of 2023 is easy. We just need to use the reverse power rule. So that means v would be x to the power of 2024 divided by 2024. Du is 1 over x. 1 over x dx. Okay. So now I just plug everything in. U times v is natural log of x times x to the power of 2024 divided by 2024. And then v is x to the power of 2024 times du. Du is x. And so, since I have x to the power of 2024 on the top and x to the power of 1 on the bottom, this simplifies to x to the power of 2023. Okay, and now I just need to find the antiderivative of x to the power of 2023 over 2024. And again, we just use the reverse power rule, and using the reverse power rule, the antiderivative is x to the power of 2024 over 2024 squared. And last, we just need a plus c. So this means that the answer to question number 9 is B. Moving on to question 10. Question 10 says, find the right formula for the work required to empty the water tank from the reverse conical tank where the radius of the top is 4 meters and the height is 10. The original depth of the water is 7 and you are only allowed to throw away the water from the top of the tank. Use density, use rho as the density of the water and g for the acceleration constant by the gravity. And it says, choose a coordinate system so that the vertex at the bottom is the origin of the y-axis. Okay. So the formula for work is the integral of F, so force, times dx. So basically, how we can think about emptying this tank is we can think about lifting each layer or thin slice of water. So we take the weight of that and then we multiply by the distance we need to move that water to find the work for each individual segment. And we take that for each thin layer of water, add that up, and that's how we get work. Okay, so first, they tell us that this point over here is the origin. So first we need to find the force, or in this case that's the weight. Okay. So for work we're going to have the integral, and we can actually start off with the bounds first. So the lower bound is going to be 0. That's kind of obvious because that's where the water is starting from. The upper bound, an easy mistake would be to say that the upper bound is 10 because the height of the cone is 10. However, the water is only up till 7 meters. So we're only moving 7 meters of water. So the upper bound is 7. And that actually gives us the answer right away. But for the sake of understanding this problem, I'm gonna explain it all out. So first we need to find an expression for the area of one layer of water. Alright, so suppose the height is y. In terms of y, we need to find out what this radius is in that case. So since we're given that the proportions of the larger cone is a radius of 4 and a height of 10, we can essentially use similar triangles to figure out the radius of this smaller circle over here. So using similar triangles, I have 4 over 10 is equal to r over y. And then solving for that means that r is equal to 4/10 y. So I'm going to say r is equal to 4/10 of y, where y is the height of the cone, which means that the area would be pi times 4/10 y squared, because pi r squared is the formula for area. So that's the area of that cone, the circle. To find the mass, all we have to do is we have to multiply by the density of water. So we multiply by rho. Okay, that's one component. The other component is the distance the water needs to travel. So in this case, if the height up till here is y, the remaining distance it needs to travel It's not a good bracket. The remaining distance it needs to travel is 10 minus y. And lastly, we need to account for the force, so we multiply by g. And you add a dy at the end. So the final expression for work is rho times g times pi times 4 over 10 y squared times 10 minus y times dy. So that means the answer to the question is D. Moving on to question 11. Question 11 says, find the volume of the solid S described below. The base of S is in the first quadrant and a quarter of a circular disk of radius 1, with the origin being the center. And the cross-section perpendicular to the base and X are squares with one side on the base. So they give us that the equation over here is x squared plus y squared equals 1. I'm going to rewrite this in terms of y. And rewriting it, I get y is equal to 1 minus x squared. Okay, so in this case, we want to find the volume of this solid. And the bounds are from x is equal to 0 to x is equal to 1, as we are shown in the diagram. Okay, and in this case, they tell us that the cross-section perpendicular to the base and x are squares with one side on the base. So one side is on the base, means that the area of each square will be f of x squared, where f of x is equal to 1 minus x squared. So f of x is the formula for the disk that they mention in the problem. So if I plug in the square root of 1 minus x squared for f of x, I get v is equal to 0, the integral from 0 to 1 of 1 minus x squared dx. Then I just have to use a reverse power rule. I get x minus x cubed over 3, from 0 to 1, and then plugging all this in, I get 1 minus 1/3, which is equal to 2/3. And that is the volume of the solid. So that means that the final answer for question 11 is C. Okay, moving on to question 12. Question 12 says, find the length of the curve y is equal to e to the power of x plus e to the power of negative x divided by 2 on the interval 0 natural log of 5. So the formula for arc length is from the x-coordinate a to x-coordinate b is the integral from a to b of 1 plus f prime of x squared dx. Okay, so first I will use this formula to solve the problem, and then at the end I'll explain where this formula comes from. Okay, so first let's find f prime of x. The derivative of e to the power of x is e to the power of x. The derivative of e to the power of negative x is negative e to the power of negative x. Okay, so plugging things in, the bounds is 0, the lower bound is 0, the upper bound is natural log of 5. And then I have 1 plus f prime of x squared, which is equal to e to the power of 2x plus e to the power of negative 2x minus 2 over 2. And this is equal to e to the power of 2x minus, e to the power of 2x plus e to the power of negative 2x over 2. Oh, I made one small mistake. This should be a 4. Okay. So now you'll notice that this expression looks almost identical to this expression, and the only difference is this negative 2 is actually a plus 2 over here. So that means that the square root of this expression is e to the power of x plus e to the power of negative x over 2. Yep. So the square root of this expression is this, which is actually just f of x. Okay, so last step now is finding the antiderivative. The antiderivative is e to the power of x minus e to the power of negative x divided by 2. And all of this is because the derivative of e to the x is just e to the x. So that makes things really easy. Okay, and then now I just plug things in. I get 5 minus 1 over 5 divided by 2 minus 1 over 2, and this is equal to 24 over 5 over 2, which is equal to 12/5. So the final answer for question 12 is D. Okay, now I'll explain where the formula from arc length comes from. So suppose I have some curve like this, and I want to estimate the length of this arc. I can consider this is delta x and this is delta y, and using Pythagorean's theorem, the length of that segment will be approximately equal to delta x squared plus delta y squared. And so the total length is just equal to the sum of a bunch of these different segments. Oh, this is y over here. Okay, so as I make delta x smaller and smaller and smaller, what I can do is I can divide both sides by delta x, and so over here I'm gonna get, so for just like one tiny length, I'm gonna get 1 plus delta y squared over delta x squared, and as dy and dx become tiny, like smaller and smaller and smaller, I get 1 plus dy dx, or f of x prime. And so now if I add this up, I can essentially rewrite it as the integral from a to b of 1 plus dy dx squared dx. And that's a really general version of how and where this formula comes from. Basically, we use the Pythagorean theorem to find the area of different like line segments, and then as we make it smaller and smaller and smaller, that's how we get this formula.